Hi, I wanted to explain to you a little bit about related rates today. In our current calculus textbook, this is section 3.11. One of the most important things about related rates is understanding the different types of variables. So a related rate problem in general has to do with something that is moving. So let's suppose we'll keep this kind of simple. We have an ice cube, right? And, I'm not draw very well, but we got this cube. And the ice cube is melting. So every single problem has some measurement that is changing in it, be it an ice cube melting, a square expanding, a circle expanding or shrinking, or think about water in a cylinder that's being drained out, or a ladder falling on the against the side of a house. So everything has something going on that's making it change. So when we talk about, so here, let me draw you a couple others. So suppose we had a cylinder and then we had water in the cylinder, right? Suppose we had a cone and we had, like one of those conical cups that you can put water in, but it has a leak and it's draining, or we're filling it up. So that water level in that cone or that cylinder or that ice cube, it's changing. And that's the important thing to remember with related rates. And everything is going to change related to time. So because it is changing, eventually we're going to differentiate. We're always going to differentiate everything with respect to time. So that being said, I want you to think of these problems. Let me add one more. Let me add the ladder problem. So suppose that's a ladder against a house, oops, that is sliding down, okay? Just so you kind of have this idea of what's going on in the various types of problems. And there's tons of problems. This is just a small sampling. So we have three different types of variables or measurements. Let's call them measurements in all of these problems. One is you may or may not have a constant. So what is a constant? A constant is the value that will never change in the problem we're talking about. So for example, when we talk about this ladder sliding down, all right, and what do you see when you see that ladder? Well, hopefully you see a triangle, a right triangle, and you might think measurements, you might think Pythagorean theorem. Normally in Pythagorean theorem, we measure things A, B, C. So I'm just going to do that for our purposes here. You can use X, Y, Z, you can use any letters you want. But the other point I'm going to drive home is when doing related rates problems, it is super important you label before you even start the problem. So that's why I'm spending some time doing this first before we jump into a couple examples. So in this problem, your C value is constant, right? As that ladder slides down, B is getting smaller. Everybody see that? A is actually going to get, because as the ladder slides down, it's also going to end up moving this way. So A is growing, B is shrinking, but C, the ladder itself never changes. That's considered a constant. So let's suppose the ladder is a 13-foot ladder. I don't even know if that exists, but let's suppose it's a 13-foot ladder. You can just have no variable there and just call it 13 feet. So anything that is a constant, the number can be placed in the problem from the beginning. From the beginning. This is important because eventually we're going to differentiate. And if you differentiate a constant, it goes to zero. So it's important to pick those constants out. Now let's talk about the ice cube. As that ice cube melts, the volume, does everyone agree, will get smaller, and the sides will get smaller. There is no constant, so we can't put anything in from the beginning. Let's take a look at our cylinder and our cone. This is a cylinder, right? And this is a cone. Well, in both of these, you have a height, correct? They both have a height. There is a radius, and because they're three-dimensional figures, we have volume, right? V for volume. Now, when we're talking about the part that's changing, we're actually talking about the liquid that's in them. So if you fill up or if you drain the cylinder, that height is either going to increase or it's going to get smaller. It's going to change. The volume of the water is going to change. So again, I'm not talking about the container. I'm talking about the water that's inside of it, the liquid that's in it. That's going to change. What stays the same in the water the whole way through? Radius. So in this problem, radius is a constant. Nothing else is a constant. So if that radius is 3 or 5 or 7, you put that number in from the very beginning. All right. Now look at your cone and think for a minute as that water drains or that water fills in that cone, is there anything that's going to be a constant? Well, the answer is no, because your radius is going to change depending on the water level. The height of the water is going to change depending on the water level, right? It's going to go up and down. The volume's going to change depending on the water level. So there's no constant. So in these examples, the only ones that have constants, the ladder and the cylinder. So I would kind of think through that problem first and find those constants. Once you have, you can put the value in. The second type of variable is just that, a variable. It's a variable measurement. For the variable measurements, you need to keep the actual variable until after you differentiate. All right, so ladder, I'll circle them in green. What are my variable measurements? Well, A and B are going to change, okay? If we had to talk about the area, that would change. In the ice cube, everything's a variable. The volume is going to change. Everything is a variable. Here is a variable measurement, volume, and the length of the sides. In our cylinder, height is a variable measurement, as is volume is a variable measurement. In our cone, height, volume, and radius are all variable measurements. So that's important to understand. But now we're going to introduce a third measurement, and that is your rate of change. So a rate of change, so think about that, is not the actual measurement, it's the rate that that measurement is changing. So it's separate from the measurement itself. So let's talk about this ladder for a minute. If we want to know the rate of change, the ladder is sliding down. So if I want rate of change the ladder is sliding down the side of the building, you need to use a derivative notation to state that. You need to use a derivative notation. And it's going to change related to time, so it's d something over dt. In this case, because our variable that is changing is b, we would call that db over dt, which is separate from the variable b. So we might say, hey, what is the rate of change? The ladder is sliding down the building when the ladder is exactly 6 feet from the ground. All right. So if I say that, I'm going to say that again. What is the rate of change? The ladder is sliding down the building when it is exactly 6 feet from the ground. That means after you differentiate, your b is at 6 feet and you're trying to find db dt. Your variable, your rate of change is always like dB dt. If you want the volume, it's dV dt. Radius, dr dt. These rates of change must always be written as a variable. So that's kind of a quick overview. I think if we jump into a couple problems, this will help you immensely. So I'm going to just take a look at a few from the book so you have all this. Let me slide down. And let's start with an example. All right, let's, I'm just grabbing some out of the textbook here. So let's, thought maybe they'd have an IceCube problem, but they don't, because that would make it easier. So I'm on page in the textbook, just so you know, 231, and I'm going to look at just number 15. Very simple. It's called an expanding circle. All right, so we have a circle. And this circle, I'm going to draw little arrows to show it's expanding. Now, it's really important if something is growing or shrinking. If it's growing or something's getting bigger, its rate of change is going to be positive. If something is getting smaller, its rate of change is going to be negative. So in this expanding circle, let's say the area of the circle increases at a rate of 1 centimeter squared per second. First thing I want you to find, how fast is the radius changing when the radius is exactly 2 centimeters. Okay, so let's figure out, what are we given? What do we have here? We have an area of a circle. So we are given increases at a rate. We are given a rate. How do you identify a rate? You got to use d something over dt. Well, because this is an area that is changing, I'm going to call that dA over dt equals 1 centimeter squared per second. So you must take the time to identify what you're given. It's going to make it so much easier. What do we want? What else are we given? We're given, oh, when r is 2 centimeters. Okay, that's not a change. Notice, radius is 2 centimeters isn't a rate of change. What are we looking for in this problem? We want How fast is the radius changing? That's a rate of change. We want the change in r with respect to t. Okay, we don't have that. All right. So after you've identified everything, please note, in this problem, is anything constant? No. As that circle increases, the radius increases, the area increases. There is no constant. Okay, there is no constant. So we can't put a constant into this problem. All right, now that we've identified everything, let's figure out what is the formula we're going to use. Well, obviously it's area of a circle. Area of circle equals pi r squared. You got to know your basic formulas for area of circle, area of a rectangle, that kind of thing. If we're you got to know your Pythagorean theorem. If we are talking about, I'll give you the volume of a cylinder, volume of a cone. Don't worry about that. But you need to know the basics. Okay, so number one. So let's kind of come up with some steps that we've done here to help us with these. Number one, identify. Identify what is given and what you want, and write it in variables like we did. Okay, number two, come up with the equation. We did that. Okay, I'm going to add a step 3 here that says put in any constant. Okay, we don't have any, so we don't need to do step 3 in this problem. After you've put in your constants, now you can differentiate. So what does that mean? We are going to use implicit differentiation with respect to t. Okay? So I'm going to do that step now. All right. Well, what's my derivative of a? My derivative of a is just 1, but because I'm doing it with respect to t, it's going to be 1 times dA dt. Pi is a constant. Please do not differentiate pi. You never want to differentiate pi. It's not a variable. It's just pi. Okay. So again, pi is just pi. Now, the derivative of r squared is 2r times dr dt. Don't forget the implicit differentiation. Unless we were differentiating the variable t, which would be dt over dt, which just equals 1, we would not need to put that there. But because we're not differentiating a variable t, and quite honestly, you're not going to differentiate a variable t in any of these problems, it's always that derivative piece, dA over dt, dr over dt, whatever it happens to be for the problem. All right, let's finish it up. So remember, let's put in what we now know. Okay, so we've done step 4, we differentiated. So step 5 is plug in what you know. So let's plug in what we know. We know dA dt is 1 centimeter squared a second equals 2 pi. We know we want dr dt when r is 2, so 2 centimeters. We don't know dr dt because that's what we want to answer in our problem, and fortunately for us, that is the only unknown we have, and all we now need to do is solve the problem. So 1 centimeter squared a second divided 2 pi times 2, 4 pi centimeters is r dr dt, and you can clean that up a little bit. you can have it as 1/4 pi. The centimeters squared up here cancels with one of these centimeters, so it ends up being centimeters per second is our dr dt. Centimeters per second makes sense for our rate. So we finished our last step, which is just solve it. Okay, so I'm going to jump into one more problem to help you kind of get the hang of it, and then I'll direct you to kind of some more examples you can look at and ones that are in your textbook. So for this one, we are going to do one of those ladder problems. So we're going to do, this is page 233. Number 41. So we have a wall and we have our ladder leaning up against this wall. Okay, so this is a 13-foot ladder. And we're going to assume that somebody is standing here and grabbing this base and pulling the foot of the ladder. So I'll read it. A 13-foot ladder is leaning against a vertical wall. When Jack begins pulling the foot of the ladder away from the wall at a rate of 0.5 feet per second. So it's being pulled at a rate of 0.5 feet per second. The question is, how fast is the top of the ladder sliding down the wall when the foot of the ladder is 5 feet from the wall? All right, how fast is the top of the ladder? So we need some variables in here. Okay, again, I see a right triangle. I want you to think Pythagorean theorem. How do you normally identify the sides of a right triangle? I tend to use A, B, C. Again, you can use any three variables you want. You can use X, Y, Z, whatever you want to do. Doesn't matter. Okay, I use A, B, C. A, B for the sides, C for the hypotenuse. So when I ask how fast is the top of the ladder sliding down the wall, they're asking for a rate. Rates get written as D something. They want to know how fast is this right here sliding down the wall. So that's the change in B related to T. All right. So we want dB dt. That's what we want in the whole problem. We are given, oh, okay, we're given a constant. Well, let's see. We are given, we want to know when this is happening when B is, not B, when the foot of the ladder is 5 feet from the wall. Well, here's your foot. Sorry, I didn't mean to erase all that. There we go. I keep hitting the eraser on my pen. There we go, that's better. Okay, so here's your foot. And they want to know all of this when this measurement right here is exactly 5 feet. So you're given A equals 5 feet as a variable. All right. What else are we given? Oh, well, wait a minute. We know the rate the ladder's being pulled away. That is the change in A. We are given dA dt, because it's the change that A is occurring, is equal to 0.5 feet per second. Okay. And now I want you to ask yourself, is there a constant anywhere? We are given the constant value of 13. Okay, that is important to know. Since that is a constant, we get to use that right away. What is the relationship? You know the relationship of a basic Pythagorean theorem is this. Okay, a squared plus b squared equals c squared. So here's the thing. Remember what we have to do. Remember our steps, which are right here. Identify what you want. Come up with an equation. Put in your constant. So before we do anything else, I'm going to get rid of that c value. A is not a constant. B, even though we have a value for B, or we have a value for A. We don't have a value for B just yet. We have a value for A. It's not a constant. So A and B stay variables. They're changing. This is a constant, 13 squared. Okay? So then I say, okay, differentiate. Well, let's do that. Sorry for the moving around. So how do I differentiate? 2a dA dt plus 2b dB dt, and hey, what's the derivative of a constant? Just 0. I didn't even have to square it. 13 squared is 169. Derivative is still 0. So let's start to put in what we know. Well, we have, this is all occurring when A is at 5 feet. We also know the rate that A is changing. dA dt is 0.5 feet per second. Ooh, we don't know B. So we're going to just leave that empty for a second. dB dt we don't expect to know because that is what we want, so we leave that as dB dt. Now, you know we can only solve an equation if we have one unknown, so we got to figure out what B is. Sometimes you're not explicitly given all the information, you need to think about it. Well, this one hopefully is pretty easy to think about it because remember, we are doing this the moment, we know that's 13 because it's a ladder. We are doing this the moment this is 5. Well, you can calculate what B is, again, using your Pythagorean theorem. 13 squared is 169 minus 25, 144, square root of 144. Just use Pythagorean theorem and you'll get 12 there. Because remember, the moment in time when A is 5, B is going to be 12. That's the value we want right here. We know B is 12, so it's 12 feet. So occasionally in these problems, you need to stop and think, ooh, I have this other unknown, but I have enough information on my problem to figure out what that other unknown is. And here's an example of that. Now look at your problem. Our only unknown is what we're looking for. We can go ahead and solve for that, right? 2 times 12, so that's 144 feet. I like to put dt. I'm moving all of this over to the other side. 2 times 5 is 10. 10 times 0.5 is 5. And yes, I know. I put 2 times 12. I put 12 squared instead of 2 times 12. I'm sorry about that. That's 24. Apologize. So, and then again, 2 times 5 is 10. 10 times 0.5 is 5. I got to move it to the other side. That's going to be negative 5. Feet times feet is feet squared per second. So dB dt, negative 5 over 24. The feet cancels one of the feet, so it's feet per second. So stop and ask yourself, does it make sense? My answer is negative. Is the value I'm looking for shrinking? Yes, this is a rate of change and it's getting smaller. The length here, B, is going to decrease. So it makes sense. So the question was, how fast is the top of the ladder sliding? It is sliding. Now, when we describe it, we don't use a negative. It's sliding at a rate of 524 I don't need the negative in my description because I use the word sliding down. That implies it is a negative rate. Okay? So these are some of the problems. You can do the, I don't want to make this video any longer than 30 minutes. What I'm also going to post for you is, sorry, my dogs are barking. So I'm also going to refer you to a video in MathLab that also has a bunch of examples you can work out. Okay?